So welcome everybody, as we say when we are learning to code hello world. Today, our speaker has made a deal with me that I'm not gonna use a background and he's going to use a background from the Atto Fridays. So we are kind of inverting the situation, and it's a pleasure to have Dr. David Ayuso from Imperial College London. He obtained his PhD from Universidad Autónoma de Madrid in 2014 under the supervision of Alicia Palacios and Fernando Martin. His PhD was also focused on the theoretical modeling of molecular photoionization and ultrafast charge migration in biologically relevant molecules, so pretty tough, initiated by ultra-short pulses. Subsequently, he went to work with Olga Smirnova at the MBI in Berlin. And then he started to look at highly nonlinear phenomena driven by intense laser fields, such as spin polarization in strong field ionization, high harmonic generation in chiral molecules. And he also looked at new ways of imaging molecular chirality on ultra-fast timescales. And last year, in fact, he joined Imperial. He was awarded a university research fellowship from the Royal Society. And this means that he now has a long-term position and he'll be able to develop his own independent research line. For those who are not familiar with this fellowship scheme in the UK, this is really, really, really hard to get. But if you get it, it's also really good, because you have resources to keep on going for a while, and you can work towards independent. And his project aims to develop new optical methods for ultra-fast and highly enantio-sensitive imaging and control of molecular chirality. And today he's going to talk about this, in fact, ultra-fast, all-optical and highly enantio-sensitive imaging of molecular chirality. And I see he likes hiking as well. If you don't believe me, look at his poster on our gallery of speakers. And he likes cats too, because he's using our background.
A really cool background.
Right, good background. So today I'm doing from my kitchen, nothing fancy, but he has the cat background. So David, the floor is yours. Feel free to start.
Thank you, Carla. Thank you so much for the nice introduction, and thank you for inviting me. Thank you, Carla, Abby, and Cornelia. I'm really happy, really excited to be with you today, even though it's not in person, but yeah, still really nice. Okay, so I'm gonna share my screen. And you can see my screen now, right?
Yes, perfect.
Great, thank you. So yeah, my talk is going to be about chirality, and it's going to be about how we can use light to distinguish between the left-handed and the right-handed version of a chiral molecule, and how can we do this efficiently and on ultra-fast timescales. So this is the outline. So first, I'm going to briefly describe what molecular chirality is and why it is so important and how it has been traditionally identified using light. Then I will present our work on synthetic chiral light, which is a new type of free propagating optical fields that enables highly efficient imaging and control of chiral matter. So with this synthetic chiral light, we can do what's illustrated in this image. So we can force one of the two enantiomers of a chiral molecule to emit bright harmonic light at new frequencies, and at the same time, the opposite enantiomer remains completely dark. Then in the second part, I will show that we can structure the chirality of light in space to realize a chiral version of Young's double-slit experiment. And I will also introduce the concept of polarization of chirality. And in the last part, I will present a new method for chiral discrimination that uses light that is confined in time and in space. And this light encodes the chirality of the molecules in the polarization of the emitted harmonic light. But before all of that, I want to acknowledge the people that have contributed to this work and also the funding. So first of all, Olga Smirnova, who has been my postdoc supervisor for 5 years at the Maxwell Institute in Berlin. Andres Ordóñez, who is a former PhD student of Olga and is now at ICFO in Barcelona. Also, we have worked with Misa Ivanov, also from the Max Planck Institute. And we collaborated in the first part of the results. We collaborated with the group of Oren Cohen in Haifa. And in the first part and in the second part of the results, we collaborated with Piero de Cleva in the calculation of photorecombination matrix elements, which this is a key component of our calculations for high harmonic generation. And we got funding from the German DFG and also from the Royal Society that supports my fellowship at Imperial. Okay, so let's start. So traditionally, there are two well-established methods for chiral discrimination for distinguishing the chirality of molecules using light. So the first one is optical rotation, which uses linearly polarized light, which is not chiral, in a chiral setup. And the second one is photo-absorption circular dichroism, which uses circularly polarized light as a chiral reagent. I'm going to talk now about circular dichroism, and I will come back to optical rotation later. So this method uses the chirality of circularly polarized light to distinguish between opposite enantiomers of a chiral molecule. And we can do this because circularly polarized is chiral, and it's chiral because it creates a helix in space. And helices are chiral. So in this method, we have, for instance, bright circularly polarized light, and we make it interact with a sample of randomly oriented right-handed molecules. And then we measure the spectrum of absorption. So we measure absorption as a function of the wavelength, as standard. Then we do the same, but instead of having right-handed molecules, we put left-handed molecules. Now, the spectrum of absorption can be different. It can be different because we have something chiral light, interacting with opposite enantiomers of the same chiral molecule. And in principle, we can use the spectra to identify the chirality of our sample and even to quantify it. But this is not so easy. It's not so easy because the differences between these two spectra are usually very tiny. And this makes chiral discrimination very challenging. And the fact that these two spectra are very similar means that the interaction between these two chiral objects are not enantio-sensitive. And the reason is that, as I said, circularly polarized light is chiral because it creates this helix in space. But the pitch of this helix is orders of magnitude larger than the molecules. So the molecules can hardly feel the chirality of the light. They can hardly feel its helicity, its chirality. So we can understand this if we use a glove, like the one I have here. You cannot see because of the background. So my hands are chiral, like the molecules. When they interact with something that is not chiral, like this mug of coffee, the interaction is the same. You cannot see. Anyway, this is a cup of coffee. So the interaction is the same because this cup of coffee is not chiral. So I can grab it with my left hand, with my right hand, exactly the same. But this glove is chiral, so it's gonna fit my right hand, but it's not going to fit my left hand. And this is chiral recognition. The same exact thing happens with molecules and light. But now imagine that this glove is 1,000 times bigger. So yeah, it's still chiral. My hands are chiral, but I could fit it in both my hands. So it would not be an efficient way of distinguishing the chirality of my hands. So it's the same with circularly polarized light. It is chiral, but this helix is way bigger than the molecules. So it's not efficient. We can look at the same thing from a different perspective. We can look at how the field evolves in space in a given point, how the field evolves in time in a given point in space. So if we look at a circularly polarized field in a given point, we're going to have the electric field vector that is going to rotate, in this case, in this direction. It will propagate in this direction. And then as a result, we get the magnetic component, which in this case will rotate in this direction. Now, this field is chiral because if we reflect it on the plane of the screen, for instance, then we get this other field where the electric field component remains the same, but now it propagates in the opposite direction. And then the magnetic field component flips in. Now, these fields are chiral because they are different. We cannot superimpose them by any rotation or by any translation. But they're chiral only when we take into account the light propagation direction and the magnetic field component. If we neglect them, then these two fields are identical, which means that circularly polarized light is not chiral within the electric dipole approximation. So with this field, The chiral response, the enantiosensitive response, can only be driven by non-dipole interactions, and in general, these are very weak, which means that circularly polarized light, again, is a poor chiral reagent because it's not chiral in the dipole approximation. And as we all know, the dominant part of the intensity of the optical response happens in the electric dipole approximation, and with this field is not enantiosensitive. And this is the reason that the spectra of left-handed and right-handed molecules with this field are almost identical. The difference are due to non-dipole effects, which in general are weak, and this can make chiral discrimination challenging. There are, of course, methods like photoelectron circular dichroism, where you can get strong enantiosensitivity with this field. So in photoelectron circular dichroism, you have a medium of randomly oriented chiral molecules, and you photoionize them with circularly polarized light. And then you measure in the direction of emission of the photoelectrons, and you can have very strong forward-backward asymmetry. So the direction of emission of photoelectrons can be very enantiosensitive. However, the total number of photoelectrons that are emitted are pretty much the same in opposite enantiomers. They're identical up to non-dipole effects. So if you want to have a strong enantiosensitivity, a strongly enantiosensitive signal at the level of total intensities, total number of electrons, total number of absorbed photons, then you need an efficient chiral reagent. And this was our motivation for developing synthetic chiral light. So as I said, circularly polarized light is a poor chiral reagent because it's not chiral in the dipole approximation. Its chirality relies on the helix that the electric field vector creates in space. To have an efficient chiral photonic reagent, we need to make light chiral in the electric dipole approximation. So what we propose is that instead of using this helix in space, we create new optical fields in which the electric field vector creates a helix in time, like this one. Although it doesn't really need to be a helix, it can be a different temporal structure that is not helical, but that is also chiral, like this one. So these would be the Lissajous figures that the tip of the electric field vector would create in time at every position in space. And these Lissajous figures, as you can see, they are 3D. They're not confined to a plane, like in the case of circularly polarized light. Here, they are 3D and they are chiral, and they're chiral in the dipole approximation. And we say that these fields are locally chiral because their chirality does not rely on the propagation direction of light. They are chiral already in the dipole approximation. And these locally chiral fields can interact with chiral matter extremely efficiently. And by controlling the temporal structure of this field, we can adjust the chirality so we can enhance the nonlinear response in one enantiomer and suppress it in the other. And I'm going to focus now in locally chiral fields that look like this one. So again, as I said, this is the Lissajous curve that the tip of the electric field vector creates in time. Now, this field is elliptically polarized at frequency omega in the XY plane, and it has a linearly polarized 2 omega component orthogonal to it along Z. So here, red means positive values of Z, blue means negative values of Z. So the field goes like this, it's elliptical, but it comes up and down of the XY plane. Now, this field is locally chiral because it will reflect this Lissajous figure. For instance, on the XY plane, now we get this other field, and in this new field, the component that rotates at frequency omega remains the same, but the Z component flip sign. And these Lissajous figures cannot be superimposed by any rotation or translation. Therefore, they're chiral, but they're chiral now in the electric dipole approximation. We don't rely on the propagation direction of light or in its spatial structure at all. And now I'm going to show how we can characterize and control the chirality of these fields, how we can generate them practically in a lab and in a way that they propagate. And then I will present numerical results for high harmonic generation in propylene oxide, and I will show that with this field you can suppress high harmonic generation in one molecule and enhance it in the opposite enantiomer. So first, how do we characterize the chirality? So the standard definitions of optical chirality vanish in the electric dipole approximation. So in order to characterize the chirality of this field, we developed a new approach, which is based on chiral correlation functions. So we did the following. First, we take snapshots of this field at 3 different times, and then we take the triple product between these vectors. And this gives us a field pseudoscalar, which has opposite sign in fields of opposite chirality. And then we take this pseudoscalar and we integrate it over the whole Lissajous figure in order to sample the whole period. And this gives us the third order chiral correlation function in the time domain. Now, we can take the Fourier transform and then get the chiral correlation function in the frequency domain. And these chiral correlation functions can only be non-zero if the field is chiral, and they have opposite phase in fields of opposite chirality. So they characterize the handedness of synthetic chiral light, but they also characterize their interaction with chiral matter. And in particular, if we look at the chiral correlation function in the frequency domain, this correlation function describes enantiosensitive 3-photon interactions in the perturbative regime. So for instance, it would describe a process where the medium absorbs 1 photon of frequency omega-1, then another photon of frequency omega-2, and then it emits a photon of frequency omega-1 plus omega-2. But the thing is that when we calculate this correlation function for this field, we get that it's 0. And indeed, in order to have a non-zero H3, you need to have at least three non-coplanar frequency components. So does this mean that this field is not chiral? Well, not really. It means that we cannot observe its chirality in nonlinear processes that involve only 3 photons. However, the chirality of this field is imprinted in higher order correlation functions. And the next chiral correlation function is H5, and it is non-zero for this field. So H5 has this form in the frequency domain. So this is the field at frequency omega, 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 and this is complex conjugate, and this is the complex conjugate of the field at frequency 2 omega. And this chiral correlation function characterizes the chirality of this field, and it also characterizes its interaction with chiral matter in the perturbative regime. And for instance, it describes and controls enantiosensitive second harmonic generation. So with this field, we have 2 multiphoton pathways that can give rise to emission at frequency 2 omega. So first, we have the first pathway, which is chiral, where the medium absorbs 3 photons from the X component, and the X component is stronger than the Y component, so we can absorb many. And then we emit 1 photon into the minor electricity component. Now, this pathway leads to polarization at frequency 2 omega, and it leads to emission of a second harmonic. This pathway is exclusive of chiral media because in isotropic non-chiral media is forbidden by symmetry, and the phase of the induced polarization is opposite in opposite molecular enantiomers. So the photons that are emitted have opposite phase in opposite enantiomers. And we also have the achiral pathway. So here the medium absorbs 1 photon of frequency 2 omega, gets polarized, and then so absorbs first the photon, gets polarized, and then emits 1 photon of frequency 2 omega. But this pathway is the same in opposite enantiomers, and this pathway is also present in non-chiral media. And the phase of this polarization is the same in opposite enantiomers, and it can be controlled with the delay between the omega and the 2 omega colors. Now the 2 pathways interfere, and then we get enantiosensitive second harmonic generation, and it gets very enantiosensitive. And it can be controlled because the phase of the polarization associated with this pathway is opposite in the opposite enantiomers. The phase associated with this pathway is the same, and it can be controlled with the phase delay. So by controlling this omega-2 omega phase delay, we can suppress second harmonic generation in one enantiomer and enhance it in the other. And it can be shown that the total intensity of emission of frequency 2 omega is given by this expression, where these are diagonal terms that don't have relative phases. This is plus for right-handed molecules, minus for left-handed molecules. Then this is the susceptibility. This is the correlation function, but here we only take the absolute values. And here, this is the interesting part. This is a molecular phase, and this is the omega-2 omega phase delay. So by controlling this, we can effectively suppress or enhance even harmonic generation in a selected enantiomer. Now, the next question, how can we generate this light practically? Well, As I said, our field is elliptically polarized at frequency omega, and it has a 2 omega frequency component that is orthogonal to the polarization of the ellipse. Now, how can we generate this field in a way that it propagates? Well, if we only have one standard laser beam, this is not possible because in one standard beam, we can have only two orthogonal polarization components that are orthogonal to the direction of propagation. And we need three. And one way we can do this is if we use a non-collinear setup. So we use two laser beams that propagate in these two directions, creating a small angle. And we're going to have omega and 2 omega polarization, omega and 2 omega frequencies orthogonally polarized in the two beams. Now, the use of non-collinear setups in nonlinear optics is not something new. This kind of setups have been used already in a number of applications, for instance, for driving chirals and frequency generation spectroscopy, for creating circularly polarized harmonics, also for doing interferometry of the Lorentz force. Here now we're going to use them to create light that is chiral in the electric dipole approximation. So, as I said, our non-collinear setup has omega and 2 omega polarization components in both beams. The omega components are linearly polarized in the plane of propagation. The 2 omega components are orthogonal to it. Now, in the overlap region, the total electric field becomes elliptically polarized at frequency omega in the plane of propagation. And it has forward ellipticity because it has ellipticity in the direction of propagation. And this is possible because the two beams are non-collinear. So this gives us our elliptically polarized field at frequency omega. Now, the 2 omega components, which are orthogonal to the plane of propagation, give us the 2 omega component that is orthogonal to the polarization of the ellipse. And now this is how we create the locally chiral field. And I tried to make it look easy, but it's not so trivial. It's not trivial first because since these two beams are non-collinear, the relative phases between them change along this direction. And we need to be very careful with this because changes in the relative phases are going to change the chirality of our field. So let's have a look. So as I said, we have two beams which propagate in the XY plane, creating a small angle with respect to Y. They are linearly polarized at frequency omega in the plane of propagation, and they are linearly polarized at frequency 2 omega orthogonal to it. And the relative phases change in this direction. And this gives us gratings. First, we have an intensity gradient. So this is the total intensity of the field as a function of this coordinate. As you can see, we have many intensity peaks where the nonlinear response will maximize. But we not only have intensity gradients, we also have phase gradients. And as I said, this is very important because they can change the chirality of our field. So how can we ensure that our field has the same chirality? Well, there are many relative phases here. Well, there are actually 3 relative phases in this setup, but there are only 2 quantities that define the chirality of our field, which are the sign of ellipticity and the phase of the 2 omega component. Because if we change the sign of the 2 omega component, you can see that we reverse the chirality of the field. Also, if we change the sign of ellipticity, we reverse the chirality of the field as well. So these 2 quantities, the sign of ellipticity and the phase of the 2 omega field, control the chirality of our locally chiral field. And they both change sign along this direction and very quickly, and there is nothing we can do about it. But what we can do is force them so they change sign exactly at the same positions. And then the chirality of the field will be conserved in space. So here we have in the values of forward ellipticity in red and the amplitude of the 2 omega field in blue. So the amplitude goes as a cosine function and ellipticity goes as a tangent function. And as you can see, what's important here is that both quantities flip sign with the same periodicity. So we just need to align these 2 gratings so they also flip sign exactly at the same positions. And this can be done by adjusting the relative phase between these 2 colors in the 2 beams. In particular, if the relative phase between the omega and the 2 omega field here and here are shifted by pi, then we get a field that has the same chirality everywhere in space. And then we can use it to enhance the response in one enantiomer and fully suppress it in the other, everywhere, all over the interaction region. And now I'm going to show you numerical results that we have for propylene oxide that demonstrate this new effect. So we have calculated high harmonic generation in propylene oxide using these laser parameters that are written here. So here we have harmonic intensity as a function of harmonic number and as a function of the emission angle for the left-handed enantiomer. And red means intensity that is polarized along Z, so in this direction, and blue means intensity that is polarized along X, so in this direction here. So the first thing that we see is that we have diffraction peaks. Harmonics are emitted in many directions, and this happens simply because in the near field we have a grating. So a grating in the near field gives us diffraction patterns in the far field. And we have even and odd harmonics. So the odd harmonics are in blue. They are polarized along X, and they're not very interesting because they are not enantiosensitive. Now, the even harmonics in red, the ones that are polarized along Z, they're extremely enantiosensitive because this is what we get in the left-handed molecule. And this is what we get in the right-handed molecule. So here we have tuned the relative strength and the relative phase of the 2 omega field. So we can enhance even harmonic generation in the left-handed molecule and fully suppress it in the right-handed molecule. And this is possible because we have an efficient chiral photonic reagent, which is chiral already in the electric dipole approximation, and because we can fully control the chirality of our field in a way that we impose that it has the same chirality everywhere in space. So with this relatively simple setup, we can produce extremely enantiosensitive intensities that in principle should be easy to detect because they are separated from the non-enantiosensitive intensities in frequency, in polarization, and in space. So they're separated in frequency because the enantiosensitive response appears at even harmonic frequencies and the non-enantiosensitive response appears at odd harmonic frequencies. They're separated in polarization because even and odd harmonics are orthogonally polarized. And they're also separated in space because even and odd harmonics are emitted in different directions. If you look at the directions of emission, they are different for even and odd harmonics. And this happens because of the different amplitude and phase gradients in the near field. I'm not going to solve this, but if you're interested, I'm happy to solve later. So this is what we get with these laser parameters. But if we now change the relative phase between the omega and the 2 omega components by pi, then we get the opposite results because then we reverse the chirality of our field. And now we can selectively suppress even harmonic generation here and enhance it here. And again, this is possible because by tuning the parameters of our beams in our setup, we can fully control the chirality of our field. And then we can decide in which enantiomer we want to enhance the signal and in which one we want to suppress it. And this new type of chirality, this local chirality, local and global chirality, opens new opportunities for imaging chiral matter and for controlling chiral molecules in a highly enantiosensitive way. Okay, now I'm going to move to the second part, and I'm going to show how we can structure the local chirality of light in space. So first, the possibility of structuring the properties of light in space at will has opened new opportunities from imaging and 3D micromanipulation to classical and quantum information. But what about structuring the chirality of light in space? Well, this actually has been considered already by several researchers. So Cameron and co-workers in Glasgow, they proposed a method for separating opposite enantiomers using structured chiral light. So they created a field whose chirality changed in space. So they use a non-collinear setup with 2 linearly polarized beams. And then the chirality of the total field would change in space. But this field was only chiral beyond the electric dipole approximation. So what they could do is then send molecules, and the molecules will be deflected in different directions. So they could use this grating of chiral light to separate opposite enantiomers of the same chiral molecule. But as I already said, this field was only chiral beyond the electric dipole approximation. And the effect that they found was in general quite weak because it was limited by the weakness of non-electric dipole interactions. Now, the question is, can we overcome this fundamental limitation using synthetic chiral light, which is chiral already within the electric dipole approximation? Well, the answer is yes. So we have seen that with this non-collinear setup that I show you, we can create a field that is locally and globally chiral. So let me remind you, local chirality means that here in the overlap region, the total electric field is chiral within the electric dipole approximation. So the least that you figure that the tip of the electric field vector creates in time is chiral. Now L stands for left-handed. We can create this field in a way that it always has the same chirality, in a way that is globally chiral. Now, by controlling the two color phase delays in the two beams, we've also seen that we can get the opposite field enantiomer. We can create a field that is right-handed everywhere in space. And we can control the local chirality of this field while forcing it to be the same everywhere in space, as I showed already. But this setup is actually quite flexible. It allows us to do something that is fundamentally different. It allows us to structure the chirality of this field in space in a non-trivial way, in a way that we create dipoles of chirality. So here, we can engineer the field so it's left-handed here, right-handed, left-handed, right-handed, left-handed, right-handed. So each of these pairs is a dipole of chirality, is a dipole of synthetic chiral light. And the total field acquires polarization of chirality. So this is in a way similar to the concept of polarization of charge. You can have a positive and a negative charge, and this creates a dipole of charge. You can have also a left-handed and right-handed chiral unit, and the pair creates a dipole of chirality. I mean, it has fundamental differences. First, because the dipole of charge is a vector, and a dipole of chirality is a pseudo-vector, but still it's a valid analogy. And by controlling the two color phase delays in the two beams, we can reverse the polarization of chirality of the field. So instead of having the left-handed unit here and the right-handed unit here, we can reverse it. So we have the left-handed unit here on the right and the right-handed unit here on the left. And then the polarization vector flips. And this is a nice new fundamental concept, but what can we do with it? Well, something that we can do is we can use this chirality polarized light to realize a chiral version of Young's double-slit experiment. So let me present the chiral double-slit experiment, which we introduced in this paper that will appear published in a few weeks in Nature.com. So this experiment involves two chiral slits of opposite chirality that emit light from different positions in space. So we have a left-handed slit and a right-handed slit. Now, in each slit, we have two contributions. So first, we have an A-chiral contribution, which is identical in the two slits. And then we also have a chiral contribution, which has the same intensity, but it has opposite phase in the two slits. Now, the A chiral contribution to emission will look like this. So the two slits will emit light with the same amplitude and phase, and therefore it will create an emission pattern that is even with respect to this direction, is symmetric. Now, the chiral contribution will look like this. So since the two slits would emit with the same intensity and opposite phase, emission will be zero in the center, and it will have opposite sign at opposite sides. Now, when we add the two contributions, since this is even and this is odd, then we'll get something that no longer is symmetric with respect to the intensity, because here the two contributions interfere constructively, and here they interfere destructively. And then we get bending of the emitted light. And what's very important is that the relative position of the two slits control the direction of bending. So this is what we get when the left-handed slit is on the left and when the right-handed slit is on the right. But if we flip their positions, then we get the opposite, because then the A chiral contribution remains exactly the same, because this is identical in the two slits, but now the chiral contributions flip. And now these two components interfere constructively here, destructively here, and then we get bending to the left. And now I'm going to show you that we can realize these Gedanken experiments using synthetic chiral light that has polarization of chirality. So let me go back to my previous slide. So we're going to use a field that has polarization of chirality. The chirality changes in space, creating these dipoles of chirality. We have calculated how a sample of randomly oriented chiral molecules interacts with this field. So here it is. This is the nonlinear response of function molecules, which is this molecule that is represented here, and this is the left-handed molecule. And then we have the results. So this is the amplitude of the nonlinear response at frequency 12 omega, so harmonic 12, as a function of x, which is the transverse coordinate, so this coordinate. And yeah, we can see that we have three. So we have groups of 3 peaks. So we have these black peaks. So black means that from these peaks, we emit harmonic 12 with phase pi. The green peak means that from this position, we emit harmonic 12 with frequency 1.5 pi. And purple means that we emit with frequency about 0.5 pi. And you can see that this is quite similar to the double slit that I was showing in the previous slide. So this emission is going to provide the A chiral reference, which is the same in the two slits. And now the chiral signal from the two slits is here, because these two contributions have the same amplitude and exactly opposite phase. So this is what we have if we put left-handed molecules here. Again, this is the nonlinear response in the near field, and these peaks are going to emit harmonic light that then we can detect in the far field. But if we change the enantiomer, then what happens? The A chiral reference peaks remain exactly the same, but now the contribution here, this chiral peak flips phase, and this chiral peak flips phase. So you can see that this means that we have changed the relative positions of the two slits. Now, what's going to happen in the far field? Well, we're going to have emission from all these slits. All this light is going to interfere. And how is it going to interfere in the far field? Well, it's not surprising. This is what we already saw. So here, when you have the right-handed slit on the left and the left-handed slit on the right, light is bent to the left. So harmonic 12 is preferentially emitted in this direction. If we put right-handed molecules instead of left-handed molecules, then we change the relative positions of the slit, and then harmonic 12 is preferentially emitted to the right. And yeah, if we can also change the position of the slits by changing the chirality, by changing the polarization of chirality of the driving field. So basically, we can realize the same thing if instead of having left-handed molecules, we put right-handed molecules, and then we flip the polarization vector of the chirality polarized field. And this new phenomenon, again, opens also new opportunities for efficient chiral discrimination and for efficient chiral recognition. It may also allow us to imprint polarization of chirality in matter that is initially achiral. Okay, now this is the last part. I'm going to introduce ultrafast optical rotation. So I was talking before about photo-absorption circular dichroism. Now I'm going to talk about traditional optical rotation. So in this method, we use linearly polarized light and we send it through a chiral medium. And then what we see is that the polarization of the wave rotates as it propagates, and it rotates in opposite directions in media of opposite chirality. So then by measuring this rotation angle, we can know whether our medium is left-handed or right-handed. Now, The main limitation is that this method relies on non-electric dipole interactions, which, as we know, they're very weak. And this poses some fundamental limitations. Now, these angles still can be quite large in optically dense media, but the single molecule contribution to this effect is really weak. So detecting the chirality of dilute samples or gas phase samples, this can be very challenging. And if you want to do ultra-fast and resource spectroscopy, then this is even more challenging. So the question is, can we design a more efficient version of this method? So I'm going to introduce an alternative version of optical rotation, which relies on a fundamentally different mechanism. Now, it also uses linearly polarized light, but it requires confinement in time and in space. And I will explain what I mean by that in a minute. And one difference with standard optical rotation is that this new method relies on nonlinear effects. So it requires higher laser intensities, and then the rotation angles appear at new harmonic frequencies. So it doesn't appear at the fundamental frequency, like in standard linear optical rotation. And what's important is that this phenomenon is driven by purely electric dipole interactions. So we can create strong rotation angles already at the single molecule response. And this opens new opportunities for then resolving chiral dynamics efficiently. So confinement in space means that the spatial region where the field is sufficiently intense needs to be small. And this is what happens in a tightly focused beam. So we need this confinement in space to create forward ellipticity. So if we have a linearly polarized field, like the one represented here, so here in red, we have the polarization vector and the field propagates in this direction. Now, near the focus, if the beam is sufficiently tight, the field acquires a longitudinal component and then it becomes elliptically polarized. And this is forward ellipticity because ellipticity is in the direction of light propagation. And this is somehow equivalent to what we can do with a non-collinear setup. But now, instead of having two beams that propagate in different directions, we create a similar effect by using a very tight focus. Now, this light with forward ellipticity, which is also called transverse beam, can drive enantio-sensitive polarization in chiral media. So if we put randomly oriented chiral molecules here, this field is going to drive at three-dimensional time-dependent polarization. So first, we're going to have a polarization component along X in this direction, which is driven by the main field component, but this component is not sensitive to chirality, so it's not interesting. Then we also have polarization along Y in this direction, but this is really the less interesting of all because it doesn't propagate, so not relevant. Now, the nice one is the one that we create orthogonal to the polarization of the ellipse, because this orthogonal polarization component is exclusive of chiral media. So in isotropic non-chiral media is symmetry forbidden, and it has opposite phase in media of opposite chirality. Now, the question is, since we have two time-dependent polarization components, which are orthogonal to the direction of propagation, this is the same in opposite enantiomers, and it has opposite phase. Now, is the combination of these two components going to create elliptically polarized harmonics with enantio-sensitive polarization? Well, in general, no, because the chiral component appears at even harmonic frequencies, and the non-chiral component appears at all harmonic frequencies, so they don't overlap. So with this field, we would create all harmonics polarized along X as usual, and then if the medium is chiral, we will also create even harmonics which will be orthogonally polarized, but always linear. Unless, of course, we use a short pulse. And this is what I meant before by confinement in time. So if we have a short pulse, which has a broad spectral band within the frequency domain, then the chiral and the non-chiral response will overlap in frequency, and then the medium will create elliptically polarized harmonics. And the polarization of these harmonics will be strongly enantio-sensitive. And as you know, if we have a very short pulse, then the phase between the carrier and the envelope, the carrier envelope phase, is very important because it determines the shape of the wave and therefore the nonlinear response of matter. And I'm going to show you now that by controlling this carrier envelope phase, we can efficiently control the optical response, the nonlinear optical response of chiral molecules with very high enantiosensitivity. So to demonstrate this effect, we have run numerical simulations for randomly oriented propylene oxide. We use time-dependent density functional theory, and we use these laser parameters. So this is the amplitude of the harmonic light emitted by the medium in the far field as a function of the harmonic number here, and as a function of the emission angle. And since we have a very short pulse, we don't have very well-defined harmonics. I mean, we do have harmonics, but they're very broad. And this is good because this is going to allow the chiral and the non-chiral response to overlap in frequency. Now, this is what we get in the left-handed molecule. And this is what we get in the right-handed molecule. As you can see, we get exactly the same. This may look like a bad thing, but it's not, and it's actually not surprising at all, or it shouldn't be, because the field that we're using to drive these harmonics is not chiral. So let me show you again the representation of the optical setup. So we are using a linearly polarized beam that becomes elliptically polarized upon tight focusing. And the minor electricity component is in the direction of propagation. But the polarization of this field is confined to the plane of the screen. Therefore, it's not chiral. And a field that is not chiral cannot generate an enantiosensitive response at the level of total intensity signals. So we indeed must get the same intensity of emission in both enantiomers. But however, as I already said, these harmonics are elliptically polarized, and it is in the polarization of these harmonics where we find the strong enantiosensitivity. So this is the ellipticity of the harmonic light emitted from the left-handed enantiomer, again, as a function of the harmonic number and as a function of the emission angle. So red means positive ellipticity, blue means negative ellipticity, and white means linear polarization. So here in the middle, harmonics are linearly polarized, and also here in this region, but they become elliptically polarized here quite quickly as we move away from the center. And as you can see, we can get quite high values of up to 60% of ellipticity. And so this is a very strong effect that is possible because we don't rely on non-electric dipole interactions. This happens already within the electric dipole approximation. And these ellipticities record the chirality of our molecules, because this is what we get in the left-handed molecule, and this is what we get in the right-handed molecule. We get exactly the opposite result. So here, negative ellipticities become positive, positive ellipticities become negative. So we can use this ellipticity to identify and even quantify the chirality of our molecules efficiently. And as you know, when we generate elliptically polarized harmonics, the polarization of the ellipses can be rotated. So let's have a look. This is the rotation angle now of the major component of the polarization ellipses for the left-handed molecule. So now blue means negative rotation angle, red means positive rotation angle, and white means no rotation. And again, I'm showing everything as a function of the harmonic number and as a function of the emission angle in the far field. Now, just to be clear, no polarization means that the main axis of the polarization of the ellipse of the harmonic is parallel to the polarization of the driving field, which is here in green. And this is what we have here for harmonic 5 and in the middle. Now, positive rotation means that the ellipse is rotated in this direction, and this is what happens here. And negative rotation means that the ellipse is rotated in the opposite direction, and this is what we see here in this region. Now, this is a purely enantiosensitive response, so I'm sure that you can already guess what's going to happen in the right-handed molecules. We get exactly the opposite result. We get exactly opposite rotation angles. So now positive rotation becomes negative, negative rotation becomes positive. And let me emphasize, these are huge values. We get rotation angles of 40, 45 degrees. So in principle, this should be relatively easy to detect. And remember that we are using very short pulse. I've shown you results for this particular CEP. And now I'm going to show you that by controlling the carrier envelope phase, we can fully control this enantiosensitive response. So to simplify the analysis, I'm going to show you the polarization of the harmonics emitted at a particular angle in the far field. So I've chosen 3 degrees, but you can see that I could have chosen 2, 4, and the results would have been quite similar. So here it is. Here we have ellipticity on the left and rotation angle on the right, emitted from in the harmonics emitted from the left-handed molecule. So as before, red here means positive ellipticity, blue means negative ellipticity, white means linear polarization. And again, I show everything as a function of harmonic number. And now the CP. This is the current envelope phase of the driving field. And now here on the right, we have the rotation angle of the polarization ellipses. So function of harmonic number and CP. And now this is positive rotation, negative rotation, and no rotation in white. So what we can see is that this chiro-optical effect is extremely sensitive to the current envelope phase because there are very strong modulations. And in particular, we can see that if we change the current envelope phase by pi, then we flip the sign of both ellipticity and both rotation angle. And this happens because if we change the CP by pi, then we are reversing the chirality of our setup. And this is already, so this is a purely enantiosensitive response. So this is what we get in the left-handed molecule. I'm sure you know already what we're going to get in the right-handed molecule. We get exactly the opposite. So yeah, the negative ellipticities become positive here, and the rotation angle also flips sign. And let me emphasize again that these are huge values for both for the ellipticity and for the rotation angle, and that we can find this in broad spectral regions. So this opens strong opportunities for enantiosensitive imaging of chiral dynamics. And we can turn this highly enantiosensitive polarization into highly enantiosensitive intensity if we put a polarizer before the detector. So this polarizer is going to project the chiral and achiral components of the harmonic light into the same axis, and then they can interfere. So they will interfere constructively in one enantiomer and destructively in the other. And this gives us a nice, strong enantiosensitive intensity. And to quantify this intensity, we can use the standard definition of chiral dichroism. So to quantify the enantiosensitivity, the intensity, sorry. So here in red, this is the intensity that we record in the left-handed molecules. In blue, this is the intensity that we record in the right-handed molecules. So we have here the difference, and this is divided by the average. So we have normalized results. And this can go from minus 200% to 200%. And here we have the values that we get. Here the polarizer is set up, it's not written in the slide, but it's 5 degrees with respect to the polarizer is 5 degrees with respect to the direction that is orthogonal to the polarization of the ellipse. And so here, yeah, we have chiral dichroism as a function of harmonic number, as a function of the CP, as before. Here we have very high values pretty much everywhere. So this red means, this strong red here means that the intensity in this region, the intensity of emission that we record from the right-handed molecules is pretty much 0. And we have a strong intensity from the left-handed molecules, and blue means the opposite. And these spectrograms are specific of each molecule. So they are molecular markers which may allow us to identify different chiral molecules in a highly enantiosensitive way. So yeah, I'm gonna go to the conclusions now. These methods that I have presented can provide very strong chiral sensitivity because they do not rely on non-electric dipole interactions. So the enantiosensitive appears already within the electric dipole approximation, and therefore it can be very strong. So this creates new ways. These are 3 new ways of imaging molecular chirality and ultrafast timescale that enable very high enantiosensitivity, as I just said, because they do know, this is a very important point, we can get such a strong enantiosensitivity because we do not rely on weak magnetic interactions. We do not rely on the helical structure that the field creates in space. So first, I introduced synthetic chiral light, and I show you that it can be generated in a way that is both locally and globally chiral, and this allows us to suppress the nonlinear response in one enantiomer and enhance it in the other everywhere in space. So we can measure strong signals from one enantiomer and nothing from the other at the level of total intensities. Now, then I showed you that we can structure the local chirality of light in a way that is no longer globally chiral, but it's something else. It becomes chirality polarized, and we create dipoles of chiral light. And these dipoles of chiral light allows us to realize a chiral version of Young's double-slit experiment. And this experiment can send light in different directions from opposite enantiomers. And then in the third part, I introduce ultrafast optical rotation. So this is a new method that uses very short and tightly focused pulses to create harmonics from chiral molecules, and these harmonics have very enantio-sensitive polarization that again can be turned into intensity with a polarizer. And I think this opens new and very exciting opportunities for ultrafast imaging of chiral molecules, chiral dynamics, and even to control chiral molecules in a highly enantio-sensitive way. And with this, I finish. So thank you very much for your attention. And if you have any questions, you want to discuss something, then I'll be very happy.
So thank you very much, David, for this really nice talk. As usual, for everybody, if you have questions, please use our Q&A or raise your hand. So we have not a question, but we have some greetings from Indian, from Narayan Prasad Agaval. Hello, good evening as well. And we have some questions from Denitsa Bayushkeva. Have you...
Hi, Denitsa.
I don't know. Okay. Have you investigated the effect of the Gowee phase shift on the chirality of the field? As in experiments, one usually works with focused beams, Q related to the part intensity and phase gratings.
Okay, so we do not, because we always assume, so to my understanding, is standard in high harmonic generation experiments that you put the molecules before the focus, so then you don't have to deal with that. So we did not include that in the calculation. So we assume that we have a very thin medium and we put the molecules before the focus. So we did not investigate the effect of the Gowee phase.
So is this okay? Would you like to inquire further, or are you happy? If you would like to talk to David, let me know. Thank you. Oh, okay, that's fine. Cheers. So we have something from Shambhu Gimayer. Hello, Shambhu, good morning in California. And he is wondering if the chiral HAG response can also be understood using possibly chiral electron trajectories. And if so, are there any limitations?
Okay. It can be understood using chiral electron trajectories. So in high harmonic generation, you have in a linearly polarized field. So you have the trajectory, electron goes and then recombines, and it's a linear trajectory. We analyze short trajectories because this can be done experimentally, and these are the ones that are more interesting because they give you access to ultra-fast time resolution. And actually we calculate chiral trajectories explicitly in this first, when we saw high harmonic generation, the first two parts, this was how it was calculated. We have quantum orbits, and these quantum orbits are chiral because the electron is driven by the chiral laser field through a chiral trajectory, and this trajectory has opposite chirality. The trajectory has opposite chirality if you reverse the chirality of the field. So this chiral trajectory can recombine efficiently in one enantiomer and not in the other. So you get enantio-sensitivity in the recombination of the chiral trajectory with the chiral ion. That's what the enantio-sensitive response comes from in high harmonic generation.
So is that fine, or would you like to inquire further?
Yeah, that's great. Thanks.
Yeah, thank you.
That's great. Thank you. We have also a question from Tahir Sharan. Thank you for your nice talk. Could you please comment on the structure of harmonic 5 and harmonic 7 in your last slide? Why does harmonic 5 have less structure than harmonic 7?
Okay. Let me go. So you mean the total intensity or in the ellipticity? Sorry, I'm not sure I understood the question.
Could you explain further? Tahir, you can unmute yourself if you wish, and if you want to ask yourself.
No, if you go to your last slides, if you don't mind.
Yes, so the ellipticity, here, this one, the last one?
Yes. And if you look at the harmonic 5 and 7, on this one, the structure is very different. I wanted to see if you could please comment on that one. Why so? Because harmonic, even harmonic is understandable. The structure is well defined, quite similar, because it's the feature of the harmonic. But when it comes to harmonic 5 and 7, we're expecting that at least the structure be kind of similar. Why is like a difference? If you can comment on that one, is that something?
Okay, yes. So yeah, I mean, the most striking thing is that here we get much higher values of chiral dichroism, and this is much weaker. This is easy to understand. So here we are projecting the chiral component, which is in this direction, and the non-chiral component, which is in this direction, by putting a polarizer that projects them onto the same direction. So to get strong enantiosensitivity, so to get strong response in one enantiomer and nothing in the other, they need to have the same intensity. And now you control the intensity in the projection with the angle between the polarizer and the propagation plane. Now, the reason you have more enantiosensitivity here than here is because for this polarization angle, the intensity of the chiral and non-chiral components are more balanced than here. But if you do a scan between of the rotation angle, then you will find that a different rotation angle, you will have much more enantiosensitivity here and not here.
Does it mean if you go to harmonic 9 is going to have the similar kind of features?
Harmonic 9, I don't remember. I think we still have harmonic 9 in this. Yeah, it could be different. Also, I mean, but what I think is also quite cool is that it's different. So this is different than this because this records the nonlinear dynamics in the molecule. So these dynamics are different at different frequencies. So.
Okay, if it's okay, I just wanted to know in your view, the wavelength and intensity is going to play a role in this, features or not? Have you looked at that, or do you think that is something which plays a role or not?
It will play a role, especially so if you look at lower order harmonics, things are going to change if you change the intensity and if you change the wavelength. Ideally, you would want to be in a wavelength where you can get in resonance with electronic states, because then that will make the chiral response stronger. Although so you want to be in resonance with some electronic states so you can get stronger chiral signal. You also want to have high intensities. Here we're using 6 × 10^13, which is similar intensities that have been used in experiments with chiral molecules. And you want to have high intensities because these are highly nonlinear effects. So you need high nonlinearities. So high intensity is important.
Thank you. Thanks for your great talk.
Thank you. Thank you. Thanks for the question.
Are there further questions, comments, anything you would like to ask us? I have one question out of curiosity. You mentioned that there are applications in quantum information of chirality and of chiral light. Could you elaborate a bit more on that?
This could be applied. What I said is that structuring the polarization of light, this has been applied to quantum information. Now, as far as I know, structuring chirality has not been applied for that, but it could open new opportunities because with chirality, you have like an extra degree of freedom. So like an extra property that you can. But yeah, I don't think I can comment any further.
Okay. No, but that's fine. It's just curiosity, and we also have a broad audience, so it's always worth asking.
Yeah.
We have something from Andre Staute. He's asking whether the focusing parameters for the nonlinear optical rotation are not unusually tight with a focal diameter of 5 micrometers. In cold streams, this is how we usually focus. Yet, we have never seen ellipticity in the photoelectron momentum distribution. Do we have any explanation for that? And just congratulating also for your talk, that it was very good.
Thanks for the question. So ellipticity in the photoelectron momentum distribution. So yeah, the thing with the, if you, the reason we want to have this very tight focusing is this. So if you, the thing is, we want to have a field that is elliptically polarized and that has the minor polarization component in the direction of propagation. And this can be achieved in several ways. One way is with the non-collinear setup. Another way is by focusing very tightly. Now, this is the reason why we want this tight focusing. Now, the question is, would be interpreting the photoelectron angular distributions of chiral molecules. So you...
Would you like to ask this live, Andre? If you would, go ahead. Feel free to talk.
So I can see now maybe where this comes from, because you seem to have opposite helicity or ellipticity in both parts of the jet. So in an experiment where you look at photoelectron distributions coming from both sides of this jet, beam, then this would cancel out, possibly.
Possibly, yeah, it could cancel out because of that. Yeah. I mean, we haven't looked at direction of photoelectrons.
I'm just wondering that you're saying that this is that there would be some ellipticity in the beam, which we have never observed. But I think this might be just the experimental inability to distinguish between the left-hand side and the right-hand side of your beam, of the laser beam.
Yeah, it could be, because I mean this happens, and this is always going to happen. The ellipticity, you have opposite ellipticity and opposite size of the beam axis. This is a fundamental property. So yeah.
Just one more comment. Amazing slides, amazing presentation. Thank you very much.
Thank you. Thank you so much.
Yeah.
Very good. We also have a question from Tobias Witting. Propylene oxide has an ionization potential of around 10 electron volts. At 6 times 10 to the 13 watts per centimeter squared, there will be a super high degree of ionization. Combining this with the tight focusing, will the high harmonic generation flux be enough for observation?
Well, ionization is high, but in the experiments that have been done in high harmonic generation in chiral molecules, they did not use tight focusing or non-collinear setup, but this is the intensity that they were using. So yeah, it ionizes, but it doesn't ionize so much, so you suppress the harmonic signal. Now, the focus will be tight, but there are also experiments where they have done with tight focusing, so I think it should be fine.
Are there any more questions? Anything anybody would like to comment? Do feel free to ask. If you would like to say hello as well, you are welcome to do so. What we're going to do now is, normally we have a live streaming and we are recording up to now. And we know some people are a bit shy. So if you would like to ask questions off record, just hang in there. And we're going to stop the streaming and the recording, and then you can have a chat with Dr. Ayuso. Let's first thank him for the really nice talk. It was a pleasure having you here. And thank you also for using our background. It's great.
It's a really cool background. And thank you again for inviting me. I'm really happy that I could be here today. Thank you.
You're welcome. And yeah, the cats are sleeping, so we won't see them, even if I don't have a background today. So everybody who is watching on YouTube, huge thanks for joining. I know there's always a bit of a lag, so I'm going to wait before I stop. But thank you for joining, for supporting the initiative. And as much as we can, we bring you nice physics every Friday. Up to next year, actually, we have a program. So thank you for supporting the Atto Fridays. And we are going to stop now. See you next week.